Hi, this is Mrs. Larson, and this lesson is on ratio, rate, and unit rate using proportional reasoning. Since this is our first video lesson, you will need to take some additional notes on how to do a video lesson. First, you'll be looking at the information on the page and you would pause. Fill in the information in your notebook, including the objective, and complete the do now. Today we're not going to go over the do now. I'll be going over that in class with you in a moment. Usually if there's a do now, the answers will be popping up when we're done. Let's go on to the next slide here. Quickly, let's talk about what a ratio is. You've seen a ratio, most of you are very familiar, that a ratio is a comparison of two quantities using division. So it can be written a variety of ways, including, as you see here, with a colon, 7 to 5, but it could also be written as 7/5. So that's 7 pieces to 5 pieces, and that's a part to part. If you have two ratios that are the same, they're equivalent ratios, they'd also make equivalent fractions. 7/5 is the same thing as 28/20. And a proportion is an equation that states two ratios are equivalent. Ratios that are equivalent are proportional, and we would put an equal sign in between the two. A rate is a type of special ratio that is a comparison of two quantities with different units. So as you can see, 90/3 is a ratio, but when you use units that are two different types, then it becomes a rate. 90 miles in 3 hours, as it says, can be read as 90 miles per 3 hours. A unit rate is a special type of rate. So that ratio we had before, 90/3 or 90 miles over 3 hours, can be simplified, dividing each by 3 to 30 miles in 1 hour or 30 miles per hour. So when you're solving it, if you look down here, you think about the information that you're looking at. So you change your ratio into a rate, meaning a comparison of two different quantities. So what kind of rate might you come up with for Jeff can type 30 words in half a minute? Well, 30 words in half a minute. And usually we put time at the bottom. It's sort of a constant piece for us. So we write 30 words in half a minute. Then we decide how we could create an equivalent fraction so we would know how to answer the question, how many words can he type in 1 minute? Well, in 1 minute, I would have to multiply that half a minute by 2. So half a minute times 2, 30 times 2 gives me 60 words a minute. That's a pretty good typing speed, actually. So you try it. Pause the screen and then write down your rate and check back in a second. Okay, let's check. Penelope can type 90 words in 2 minutes. Yep, you're right, 90 words over 2 minutes. Now to determine the unit rate, how many words she can type in 1 minute. Okay, we're back. Yes, divide the numerator and denominator by 2 because we want 1 minute, and it's 45 words per minute. Well done. Let's try another one. This time we're going to be talking about something you see in science, which is density. And density measures the mass of something compared to its volume. So we say density is mass divided by volume. And the units for density are written in kilograms per meters cubed. This is actually supposed to be an exponent. So here it says 5 cubic meters of copper has a mass of 54,800 kilograms. And we're trying to find the density. So over here, 5 cubic meters, is that the volume? Yes, look, cubic meters is the same thing as meters cubed. So don't be confused by that. Cubic meters is the same as meters cubed. So if density is mass divided by volume, take a second to try and use the numerical values for mass and volume. Right, let's see. Right, 44,800 kilograms, that's the mass. It says up here the mass. And here's the volume, 5 cubic meters or meters cubed. So here's my density, but again, this is not in a unit rate. We want to find the actual density of the copper. In order to do that, we want literally in kilograms per 1 meter cubed. So we want to get that to a 1. Take a second to do the division and find out what the density of this copper is. Okay, welcome back. Here we go. We take our original rate, divide the numerator and denominator by 5 because we want to get this to 1. So our denominator is now 1 cubic meter. And when we divide our numerator by 5, it's 8,960 kilograms. So we would say that the density of copper is 8,960 kilograms per meters cubed. So that's a correct density notation. I'd like you to try this one. So I'll read it, pause the screen, and then you try it, and when you unpause, we'll reveal the answer. A piece of gold with a volume of 5/10 cubic meters weighs 9,650 kilograms. What is the density of gold? Again, the reminder is density equals the mass divided by the volume. Take a minute to pause and try and solve this problem. Okay, well, hopefully you first wrote out the unit, the rates here, 9,650 kilograms and 5/10 meters cubed. Then, in order to solve this, you would have to double the meters cubed, so you could get 1 meter cubed, and double the kilograms. So yes, you have 19,300 kilograms per meter cubed, and that's the density of this piece of gold. Well done. All right, next we're going to talk about a similar type of rate, and this is actually a rate. Rate, in this case, is the distance divided by the time. So this is a very familiar piece of information that you'll see over and over again when you're talking about miles per hour, etc. That's called a rate. And rate is distance over time or distance divided by time. So similar to our density formula, if you want to determine the average speed, that's obviously talking about miles per hour. So use the information and try to determine the driver's speed. So the driver is competing in a 500-mile auto race. In the first 2 hours of the race, the driver travels 356 miles. So are you going to use the 500 or the 356? Don't be fooled by the additional piece of information. Yes, he's competing in a 500-mile auto race, but he's actually traveling a distance of 356 miles, which is right here. So when you write your rate, make sure that you use the correct information. 356 miles is how far he went, or the distance, in 2 hours. And to determine the average miles per hour, divide the numerator and denominator by 2, and we have 178 miles per hour, which is remarkably fast. I'm not quite sure what kind of car he's driving, but holy mackerel. So the driver's average speed is 178 miles per hour. Pretty fast. So this is the same driver, same race, and he's competing in this 500-mile auto race, and he's making an estimate. He figures after he did the 2 hours, he's like, oh, I'm gonna finish the race in less than 3 hours if he's traveling at the same average speed. Is this reasonable? Well, let's go back just to make sure you remember that his average speed is 178 miles per hour. I want you to use that information here. So what is your rate? Your rate is 178 miles per hour. How can you determine if 3 hours or less than 3 hours is going to be a reasonable amount of time? Well, instead of 1 hour, right, you're going to want to multiply the numerator and denominator by 3. So 1 hour becomes 3 hours, 178 miles becomes 534 miles. And yes, completing a 500-mile auto race could be done in less than 3 hours. Not much less, but yes, less than 3 hours. So let's do one last piece here. We have the 70-mile bike race. First 2 hours of the race, the cyclist travels 14 miles. What is the average speed? Take a minute to pause, solve this problem, and then click back on and we'll see if you were right. Okay, let's check. Did you get a rate of 14 miles in 2 hours? Great. Now let's check your work. 14 miles in 2 hours gives you 7 miles per hour. That's the average speed. Similar to a unit rate is a unit price. Same idea. We've got two different kinds of information. In this case, the price of an item and the number of ounces that are in that item. So when we're doing a unit rate for a unit price, we're comparing one unit of that item to the price. So the unit is always on the bottom, the price is always on the top. A unit price always has the dollar amount on the top. So this is written $2.19 for 15 ounces, or $2.78 for 20 ounces. And this is where you have to utilize your decimal division and say, what is 219 divided by 15? Well, that's about 0.146 cents per ounce. Obviously, that's going to round up to 15. And this one's rounding to about 14. So the better buy is our 20-ounce jar, because although it costs more in the beginning, we pay less per ounce. If you go to the grocery store, you'll notice usually on the left-hand side of the price, it'll tell you the unit price. And that's a better way to compare prices at the grocery store. So try one of these on your own. I think some of you play golf. So golf balls can be purchased in a 3-pack for $4.95 or a 12-pack for $18.95. And which is the better buy? So pause for a moment. What I want you to do is set up your two unit price comparisons, then do the division, and then determine the better buy. And then come back in and we'll check. All right, let's check. Here are our two unit rate comparisons, $4.95 for a 3-pack, $18.95 for a 12-pack. We divide here by 3, the numerator and denominator, and for our 12-pack, we're dividing by 12. So it turns out that the 3-pack costs $1.65 per pack, and the 12-pack is only $1.58. So even though we're buying more golf balls, we're better off as a unit rate over the long term, paying for the 12-pack at $1.58. Finally, today what you need to do is take a minute and complete these questions. You can certainly print them out if you'd like, and then answer the questions in your notes. Congratulations!